Superposition of magnetic fields. Each of the two wires in the figure carries an identical current I into the page. So you can see the figure, and we've indicated that the current is into the page with the X's. At which location will the B field do all of these things? At each of these 5 points, which are just random points in space, the magnetic field there is going to be the superposition of the magnetic field contribution from the left wire as well as the contribution from the right wire. What we need to keep in mind here is the Thumbkin-Twiston right-hand rule. Here's my little model for it, which says that you point your right thumb in the direction that the current is moving, or the positive charge is moving, and then your fingers curl in the direction that the field lines would go. For the current on the right here, which is going into the page, see if I've got my current going into the page, then my fingers are going to curl in that direction. At point E, due to this wire, there's going to be a downward contribution to the magnetic field. What about at the same point, I'm keeping my finger on it, from this wire? Well, it'll also be at E, it'll be downward, but it'll be weaker, won't it? But in any case, it will definitely be downward. Point towards the bottom of the page, letter E, for sure. How about at point A? Well, at point A, let's do the left wire. Now we're going into the page, and at A, it's going to be upward contribution. And how about due to this one? Also upward at A, but weaker, but towards the top of the page. There you go. How about at C? Due to the wire on the right, at C, there's going to be an upward contribution, and due to the wire on the left, at point C, downward. Those are going to exactly cancel. If C is right in the middle and those two currents are equal, there will be no magnetic field right there at point C. What about at point B? Well, at point B, we're going to be directed which way? From the current on the right, there's going to be a magnetic field contribution that is directed like that. How about due to the wire on the left? From the wire on the left, we're using our right-hand rule. At point B, can you visualize this? Woof, down and to the right, kind of like this. And what happens is the up and the down components of these cancel, but the two to the right add up. At point B, this magnetic field will point directly to the right. What about at point D? At point D, let's do the wire on the left first. At point D, due to the wire on the left, we're going to get a magnetic field contribution directed like so. And due to the wire on the right, we're going to get a magnetic field contribution at point D that is directed in this direction. I hope you can see that. The up and downs cancel, and that means that this net magnetic field is going to point directly to the left. Now we're going to do the same thing, except this time the wires have currents that are equal, but they're pointing in the opposite direction of each other. Let's talk about point Z first. From point Z, due to the wire on the right, we're going to get an upward contribution. And at point Z, due to the wire on the left, we're going to get a downward contribution, but the downward one is going to be weaker because it's further away from the left wire. So I think upward is going to win, and at Z, we're going straight up to the top of the page. How about at X? At X, we're getting a downward contribution due to the wire on the right, and we're getting another downward contribution due to the wire on the left. Use your right-hand rule. Should we do that once for you with our little model here? The wire on the right, we're coming out of the page now. So at point X, pointing down, due to the wire on the left, also pointing down. So towards the bottom of the page, point X. How about point V? Point V, that one we're getting an upward contribution due to this wire, and we're getting a downward contribution at V due to the wire on the right, but the downward is weaker. So at point V, it's going to be pointing towards the top of the page. At W, due to the wire on the left, we're going to get a contribution that looks like that. And due to the wire on the right, we're going to get a contribution. We're using our thumbkin twist and right hand rule that looks like that. So the left and rights cancel, and this is going to be directly towards the bottom of the page at point W. What about at point Y? That's the only one we haven't done yet. So at point Y, due to the wire on the right, we're going to get a magnetic field contribution that's directed that way. And due to the wire on the left, we're going to get a magnetic field contribution that way. The left and the rights cancel towards the bottom of the page. For this case, where's the magnetic field equal to 0? None of those places. Where does it point to the left? None of those places. To the right? None of those places. Now these are our last two. This is a rehash of the two previous ones. How do the magnetic field strengths compare? A compared to E. Well, let's see. At E, we have downward contribution pretty big, and then downward contribution smaller. And at A, we have upward contribution pretty big due to this wire, and upward contribution pretty small due to that, but won't their magnitudes be equal? You try and convince yourself of that. How about X compared to Y? X compared to Y, there we go. At X compared to Y, at Y, it's going to be downward towards the bottom of the page. And at X, it's going to be downward towards the bottom of the page, but which is going to have the stronger magnetic field? It's going to be X, because it's closer to each of those wires. So X is going to be greater. How about B compared to D? B compared to D, they are equidistant from each of these wires, and B, we said, is going to be directed which way did we say? B is towards the right, and D is to the left, but won't they have the same magnitude as each other? You work your way through that if you need to. How about V compared to Z? V compared to Z. Z, we have an upward contribution that's big due to I, and upward contribution due to I that's pretty big, and a downward contribution for this I. At V, we have an upward contribution that's pretty big, and then a downward contribution that's smaller. Those are equal to each other, aren't they? All right, last one, A compared to V. A is over here, V is over here. V, you see there's a canceling effect. What about at A? This is the far left side of the screen. At A, we have a rather big contribution due to the close wire that's pointed up, and then we have a rather small contribution due to the wire on the right. So the magnitude of the field at point A compared to point V is going to be bigger.